Well, first of all, I want to show you a different formulation for average rate of change. We've kind of looked at average rate of change for a function being the function's value at b minus the function's value at a. That's the difference in the y's, because the function's value, the outputs are the y's, divided by b minus a. That's what we've been doing for average rate of change, making it sort of look like that slope formula. And we talked about it being the slope of the secant line. Well, here what we want to do is I want to think about b not being a different, well, b is a different number, but instead of calling it b, I want b to be equal to a plus a little bit, called h. Okay, and in other words, we were looking at the problems before, we were looking at going from 1 to 3, or 7 to 12. But what I want to do now is I want to look at my other point as being some number of units away from A. Okay? So I'm looking at the other number being related to A by being plus a little bit, B plus a little bit. So what this ends up looking like, so instead of having the B, we're going to write in A plus a little bit, A plus H being our little bit, minus F evaluated at A. In the denominator, let's see what's going to happen here. We're going to have, instead of B, we're going to write in A plus H, okay, minus A. So what do we get in the denominator? We'll just have an H. In other words, what was always in the denominator, the delta x, is how far apart those two values were anyways. That's what H is. H is how far apart those two different numbers are. Okay? If it was 7 and 12, the H is 5, because they were 5 units away from each other. If it was 1 and 3, the H is 2, because they were 2 units away from each other. So when you did that subtraction, you found out how far apart those two numbers were. That's the delta x. So now, in this formulation of it, we just leave the delta x as the h. That's how far apart A is from B. And we call that the difference quotient. That's what we see over here. Now I had A here. This is in terms of a general function f with a variable x. That's called our difference quotient. It's a different way to look at average rate of change. So the next exercise that you'll have to do would be just to compute these. Make sure you know how to compute these algebraically for some different functions. So let's compute the difference quotient. Oh, you guys need, I guess what I have for you. I do have these run off. Go down and get those. So what we have to do here is, in fact, I want to go for it and go back so I can have it to work on. So if we want to compute the difference quotient for this function, just want to get you familiar with that, what that is first. We have to find out what the function evaluated at x plus h is. That'll be an expression in terms of x and h. And then we have to find out what the function evaluated at x is, which we've got that, divided by h. So if we take this function, x, 8 minus 3x squared, and we want to evaluate the function at x plus h, our input is the expression x plus h. So we're in x plus h here and here. Okay? So we have to simplify that algebraically. Let's look at some rules of algebra here. Order of operations. Got to square before we can multiply 3 by 3. So when we square that binomial, what are we going to get? X squared. Okay. Yay! That's what I was wanting to hear. When you square that binomial, you get a trinomial out. 2xh plus h squared. Because it's x plus h times x plus h, and make sure you FOIL it out, or you square the binomial. That would be the correct expression for this one. So it's 3x squared minus 6xh minus 3h squared. That would be our 4 terms. And there's no like terms. That is the function evaluated at x plus h. So we're ready to do the difference quotient, called dq. The difference quotient. This expression, dq, yeah, really, make us all hungry, think of Dairy Queen. That expression is what we're going to put in for f evaluated at x plus h. That's going to go into the difference quotient for that. Those 4 terms will be what we've got for f evaluated at x plus h. Some algebraic manipulation here, yes. So we've got that. Minus, right, exactly. So Jamie saw what we need to do now. So when we want to do the next step, or our difference quotient, it's f evaluated at x plus h. It's this minus the original function, f evaluated at x. Okay, so we're going to take that, we're going to plug in f evaluated at x, and we're going to put in the original function, 8 minus 3x squared. And then we can simplify, and we divide everything by h. So now we're going to do some algebra here to get this difference quotient simplified. So we're going to get 8 minus 3x squared minus 6xh minus 3h squared minus 8 plus 3x squared divided by h. Some terms go away, at least the 8's go away, the 3x squareds go away. So our,
f of x
yeah, it does. And all that's left are the 2 terms involving h. So that's going to be negative 6xh minus 3h squared. So our dq here equals negative 6xh minus h squared divided by 3h squared, right? Yeah, 3h squared. dq negative 6xh minus 3h squared divided by h. Okay, we can do some more simplification because we can factor out at h. And we're going to get negative 6x minus 3h divided by h. h's cancel. There's the difference quotient. Is negative 6x minus 3h. Okay? Let me capture that so if you have questions about what I did, I can go back to that previous screen. There's some practice in your book for this. I'm going to give you another one so that I can go downstairs and get the copies I forgot. So these go back to, again, we're trying to pull back from some of the beginning of this book. Pick out another one here. No. If you look at your homework list, you can see some difference quotient ones too. I have to find them. Okay. Look at page 127. Number 42. And you'll have to find difference quotient for this function, f of x equals 2 minus 3x. And remember what difference quotient is. Function evaluated at x plus h minus the function evaluated at x divided by h. You want to try that while I run down there? Yes. So when we look at this one, this is f evaluated at x plus h. Think about you're taking your function, 2 minus 3, and evaluated it at x plus h.
with no square.
Right. Because this function is a linear function, 2 minus 3x. So you would get f evaluated at x plus h would be 2 minus 3x minus 3h. So now our difference quotient is going to be that expression, 2 minus 3x minus 3h, minus the original function, 2 minus 3x, divided by h. Okay? So we're figuring out, well, good, I'm glad y'all tried it first. Sometimes that's better. It's better for you guys to try, see those things that can cause you confusion, and then...
I was like, where does the 3x squared go? It's really everything. I was just going to annihilate it anyways. I was going to mark it off.
Since I run out of space, we're all okay there. If you subtract 2, the 2's drop off, the 3x's drop off. So the h's will cancel. So you get, this is negative 3 for our difference quotient. All right. So some of your homework this weekend, you'll have some practice doing that. Okay? Yes, sir.
Usually in the application, it'll say different quotients
Yes.
within the...
Well, actually, it doesn't say, it doesn't use that vocabulary. I wish it did. Some other books do. It'll say calculate this.
Oh, it just shows you...
It shows you this,
yeah,
this formulation. That's difference quotient. Yeah, some books will say difference quotient. Some don't. But you also have it now on the front page of that handout I just gave you. All right, so where are we going from here then? Okay, now what we got to do, we got to tie average rate of change to difference quotient. I'm going to show you how that's going to happen. Okay, but Reggie looks like he might still have a question.
So I could say, how did you know 3? I thought it was, negative 3. I thought it was probably 3.
Well, what happened here is, okay, I got 2 minus 2, the 2's cancel. Negative 3x plus positive 3x, 3x's cancel. So the only term that's left in the numerator is a negative 3h. And then I have an h factor in the denominator, and they cancel. And that's how I get my negative 3.
You made x minus h.
Okay, good. That's what we have to find out. All right, so next, turn the next page and look at this bacteria population graph I gave you. Because what we were finding with the secant lines is the average rate of change, and there's a big jump. And remember how you guys made the observations that if you change the secant lines, the average rate of change changes. Well, it might be a good question to ask ourselves. A question that we might want to ask would be, how could we get closer and closer to how the function is changing at a particular point? What is the rate of change, not over an interval, but at a single point in time? Okay? Well, the way that we're going to do that is we're going to make our numbers, our secant lines, get closer and closer. Let's look at this one in red. This one will be a red secant line. Okay, the red secant line. I want to look at the average rate of change from 3 to 4. So where would that be? From 3 to 4. That's going to be this secant line. And we can compute that slope of that secant line. And that would be the average rate of change of this bacteria population between time 3 minutes and 4 minutes. Right here. So let's do that. That slope of that red secant line would be, let's go with 2 minus 4.2, 4 minus 3. 3 to 3 plus 1. So what's the denominator going to be? The h value is going to be the same thing that we have here. 3 to 3 plus 1. 3 to 3 plus 1. And then in the numerator we're going to get 2 minus 4.2 would be a negative 1.8. If I add 8 tenths, that 1, I get 4. No, are we sure?
Yes.
Okay. My brain is now fried, so if you did on your calculator, I believe you. If I had $2 and I spent $4.20, I'd be in trouble. Isn't that right? 2.2. Okay. Thank you. I was going to say, all right. So that was my red secant line. Well, let's do a green secant line. Now, let's go from 3 to 3 plus a half. So what two numbers is that between? That's between what and what? Between x equals our time of 3 and 3.5 minutes. So where would that be? So this is 3.5. So I'm looking at 3 to 3.5. So where does that fall on my graph? About right here?
No, a little higher up.
3.5. There's my.
Is it hit about
Okay, right there?
The 3 mark?
Okay.
3
All right.
by 3?
Yeah. That'll give us a better estimation then. Because this is a visual right now, so we're still estimating. But look at that tangent. Look at that secant line. It's going to be hard to draw on here. I want to go through those 2 points on the graph between 3 and 3.5. Okay, so what's the slope there going to be? Well, that's going to be 3 minus 4.2 divided by 3.5 minus 3. So we have our little bit here is now smaller. Instead of being 1 unit away from each other, they're half a unit away from each other. All right, now I got to do this subtraction in my head. 3 minus 4.2. 1.2, negative 1.2. Okay, and so negative 1.2 divided by 0.5 would be a negative 2.4. That's dividing by half, which is multiplying by 2. So I can do that one mentally without checking my calculator. Okay? The idea here, and I know I'm almost out of time, what I'm after showing you here is that it seems reasonable now, as we find average rates of change that are shorter and shorter time periods between 3 and something else. As we get closer and closer to 3. So we did from 3 to 4, then from 3 to 3.5. Then if we had more time, I would go from 3 to 3.25. Then you could go from 3 to 3.01. You could get your graph where you could get a good reading from the graph for that. If we get closer and closer to that, we should be getting something that's reasonable for us to say, what is the rate of change at exactly 3?
What about the difference quotient?
That's what. Well, we had remember, difference quotient is a different way to look at average rate of change.
Oh, okay.
We want to make the h values smaller and smaller and smaller. What's the language that we've talked about for that? A limit, right? If we want to know what is the rate of change, how is the function changing at exactly 3 units, we can take a limit. We can look at this, look at the back. We call this the instantaneous rate of change. At a single point, instead of looking at over a time interval, at a single point in time, how is that function changing? That involves letting these h values get very, very, very small, letting h go to 0. So limit as h goes to 0, there's that difference quotient again. So the instantaneous rate of change, not over an interval, but at a certain instant in time, is this limit value.